Welcome to the primary flight controls lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: general overview of an aircraft's three principal axes and the control surfaces that act on each one of them, basic physics of control surfaces, primary flight controls on the 737 NGX for pitch, roll, and yaw. We'll also be discussing their relationship with the hydraulic systems and the standby hydraulic system, horizontal stabilizer trim, flight spoilers, and yaw damper, Mach trim system and speed trim system, 737 NG flight controls system components, and a lesson summary. An aircraft's attitude can be changed around three perpendicular axes that intersect at the center of gravity, or CG: lateral axis, longitudinal axis, and vertical axis. External forces like wind may alter the desired flight path, thus creating the need for the aircraft to be maneuvered back to the correct attitude through three movements: pitch around the lateral axis, roll around the longitudinal axis, or yaw around the vertical axis. To achieve these movements around the aircraft's axes, flight controls are employed. There are two groups of flight controls: primary and secondary. Secondary flight controls are covered in the secondary flight controls lesson. The primary flight control surfaces and their direct effects are elevators, change in pitch, ailerons, change in roll, or rudder, change in yaw. An aircraft is free to rotate within the three axes and will always turn about its CG, or center of gravity. The tendency to do this is known as a turning moment. A moment is equal to the product of the force applied and the distance from which the force is being applied. This is known as arm, and it's measured with reference to a defined datum. Because the relationship between force and arm is inversely proportional, the longer the distance from the datum means the force has to be smaller to maintain positive balance, and vice versa. The flight controls are designed to deflect airflow and produce these forces that make the aircraft turn around its axes. This is done by changing the angle of attack of the control surface, thus allowing for a change in lift. For example, when the control column is pulled back, the elevators are deflected upwards, and due to the lower angle of attack on the control surface, there is lesser lift in the horizontal stabilizer, causing it to go down and thus bringing the aircraft nose up. The 737 NG has two elevators, two ailerons, one rudder, and 8 flight spoilers. We'll now split this lesson into pitch, roll, and yaw. Elevators are movable surfaces attached to the rear spar on the trailing edge of the horizontal stabilizer that control the pitch attitude of the aircraft around its lateral axis. The pilot moves the control column forward or aft to achieve the desired change in attitude. Paired cables are used to transmit pilot input into the respective interfaces and flight control surfaces. In order to provide system redundancy, each hydraulic system, A and B, powers one of the two elevators on the 737 NGX. Either hydraulic system may power both elevators in case one of the two systems fails. The basic principle is the control column sends the pilot's inputs to the Elevator Power Control Unit, or PCU, which is an interface between the pilot's mechanical input and a series of hydraulic actuators on each elevator. These inputs are also sent to the Flight Data Acquisition Unit, or FDAU, for flight data recording. The autopilots have a separate series of actuators that also give mechanical input to the elevator PCUs. The right PCU gets hydraulic system B pressure, and the left PCU gets system A pressure. This means either hydraulic system may command both elevators in case one of the two systems fails. The PCUs ensure that the elevators may always be moved under any condition. This means that even in the event of a complete hydraulic failure, the cables and linkages allow for manual operation of the elevators. This condition is known as manual reversion. In case one of the control columns becomes jammed, elevator control is still achievable from the other control column thanks to the elevator breakout mechanism. This provides added reliability and system redundancy. At least 31 pounds of additional force must be applied to use the working control column while the other is jammed. In this condition, when 100 pounds of force are applied on the control column, the elevator moves 4 degrees. In a total hydraulic failure emergency situation, this amount of deflection is sufficient for a safe landing flare. The elevator PCUs also limit the amount of elevator travel. When the horizontal stabilizer is neutral and there's no input to the mock trim actuator, which will be discussed further along, the elevator is downrigged 4 degrees, with reference to the stabilizer mean chord line. From this position, the elevator can move 24.3 degrees up and 18.1 degrees down. Each elevator has 3 balance panels, with balance weights in the forward side and a tab attached to the aft edge. The balance panels decrease the force necessary to move the elevator in flight. The elevator feel and centering unit is a computer that gives variable control column forces as the airspeed changes and the horizontal stabilizer moves. The elevator feel computer receives input from pitot tubes through pitot ports, hydraulic system A and B, horizontal stabilizer, elevator feel shift module, or EFSM. This last mechanism operates during a stall, providing 850 psi of hydraulic system A pressure to the elevator feel system. Elevator feel and centering also moves the elevators to a neutral position when there's no input. When the control column moves, a roller is moved, causing springs to extend and provide a feel force. When the control column is released, the roller moves to a detent, and thus the system moves to a neutral position. At higher airspeeds, the elevator feel computer increases the metered pressure to the control column feel system to provide simulated aerodynamic forces when operating the control columns. This feature is not available during manual reversion. The elevators also have a tab that varies to help reduce the required elevator pitching moment. When the trailing edge flaps are up, the elevator tab operates in balance mode. The tab moves in a direction opposite to elevator travel. When the trailing edge flaps are not up and there is hydraulic power, the elevator tab operates in anti-balance mode. The tab moves in the same direction of elevator travel. Most aircraft have little surfaces on the flight controls that are utilized to hold the aircraft in its current attitude without the pilot having to make excessive input on the control systems. This process is known as trimming the aircraft, and the 737 NGX is trimmable in all 3 of the primary flight controls. The pitch trim is controlled with a movable horizontal stabilizer by any of 3 ways: manual operation with the stabilizer trim wheels, electric operation with the stabilizer trim switches, or autopilot operation, achieved electronically through a digital flight control system, or DFCS. During manual operation, the pilots use stabilizer trim wheels that are linked to a mechanism with a jack screw. When the jack screw moves, the horizontal stabilizer moves. It's good to know that under normal conditions, the stabilizer trim is the only control surface on the 737 NG that's completely independent from the need of hydraulic power. This also means that under certain flight conditions, the effort required to manually operate the stabilizer trim may be higher. During electric operation, the pilots operate 4 stabilizer trim switches located on the outboard side of each control wheel. These control electric input to the stabilizer trim actuator that also moves a mechanism with a jack screw. Like we mentioned before, when the jack screw moves, the stabilizer moves. The system is made so that when the electric stabilizer switch is operated, the horizontal stabilizer is moved, and so are the stabilizer trim wheels. In case the stabilizer is trimmed to the end of its electric limits, additional trim is available through the manual trim wheels. Finally, during autopilot operation, the digital flight control system gives electric input to the stabilizer trim actuator. However, this actuator operates at different speeds when receiving autopilot input. Stabilizer position sensors feed the DFCS. Sensor A sends information to the DCFS via the Flight Control Computer, FCC, A. And similarly for sensor B. There are various switches associated to stabilizer trim operation. Column cutout switches, stabilizer trim override switch, stabilizer trim cutout switches, flaps up switch, stabilizer trim limit switches. The column cutout switches allow for the stabilizer trim to stop in case the pilot electrically trims the stabilizer opposite to elevator control input. The stabilizer trim override switch bypasses the column cutout switch. The pilot uses this switch to operate the electric trim if both column cutout switches fail. The stabilizer trim cutout switches are used to stop the stabilizer trim actuator if there's any uncommanded motion of the trim actuator. The flaps up switch determines trim speed relative to flap position. When the flaps are up, low-speed trim is engaged at 0.2 units per second. When flaps are not up, high-speed trim is engaged at 0.4 units per second. The stabilizer trim limit switches limit the range of stabilizer travel. There are different limits for manual, autopilot, flaps up, or flaps down operation. There's also a takeoff warning switch that alerts for incorrect stabilizer trim configuration during takeoff. The cockpit stabilizer trim indicator has a green band to show the takeoff trim range. The horizontal stabilizer movement lower and higher limits, as well as the neutral position, are marked on the fuselage. The limits are 4.2 degrees of stabilizer leading edge up, 12.9 degrees of stabilizer leading edge down. It's good to keep in mind that when the stabilizer moves up, the aircraft nose moves down, and vice versa. We've mentioned the Mach trim system a couple of times during this lesson. This will be explained now. Mach number is the relationship between the true airspeed of an aircraft and speed of sound. If the Mach number exceeds 1, the aircraft becomes supersonic. The 737 NGX has a maximum cruising speed of Mach 0.780. The Mach trim system provides speed stability at Mach numbers above 0.615. Elevators are adjusted relative to stabilizer position as speed increases, subsequently changing the control column neutral position through the elevator feel and centering unit. The Mach information is obtained from the Air Data Inertial Reference Unit, or ADIRU. Another similar system in the 737 NGX is the speed trim system. Like the Mach trim system, the speed trim system also provides speed stability. However, it's designed to return the aircraft to a trimmed speed by trimming the stabilizer opposite to the direction of speed change. This also increases control column forces. Some conditions that have to be met for speed trim operation are low gross weight, aft center of gravity, N1 greater than 60% or high power settings, airspeed between 100 indicated knots and Mach 0.50, and autopilot disengaged. Essentially, when the speed trim system comes alive, it requires the pilot to provide a significant amount of pull force to reduce airspeed and significant amount of push force to increase airspeed. You can see that there are quite a few ways that the elevator controls translate to direct and comfortable pilot control. Although quite complex, this elevator system is relatively simple compared to other aircraft flight control systems. Ailerons are movable surfaces on both wing outboard trailing edges that control the flight attitude of the aircraft about the longitudinal axis, more commonly known as roll. The ailerons are coupled so that when one of them moves down, the other moves up. There are 3 ways of achieving roll control on the 737NG. Manually, by moving either control wheel; automatically, by autopilot input to move control wheels with actuators; or through flight spoilers. These will be discussed at a further stage during this lesson. During manual operation, the flight crew controls the roll attitude with control wheels that are interlinked mechanically in order to provide system redundancy. Just like with the elevators, the ailerons are actuated through pairs of cables that transmit force. Ailerons are also operated via the Aileron Power Control Unit, or PCU, that acts as an interface between the pilot's mechanical inputs and a series of hydraulic actuators that move the ailerons with wing cables. The aileron PCUs ensure that the ailerons are movable under any condition. Under normal operation, each hydraulic system controls a single aileron. In case of a hydraulic system failure, the working system may control both ailerons. In case of a total hydraulic failure, ailerons are still controllable mechanically. This condition is known as manual reversion. The upper PCU gets hydraulic system B pressure, and the lower PCU gets hydraulic system A pressure. The PCUs also limit aileron travel to 20 degrees up and 15 degrees down. When pilots turn the control wheels, mechanical stops in the aileron control wheel components keep the control wheel movement limited to 107.5 degrees left or right. The aileron feel and centering move the ailerons to a neutral position when there is no input. When the control column moves, a roller is moved, causing springs to extend and provide a feel force. When the control column is released, the roller moves to a detent, and thus the system moves to a neutral position. The captain's control wheel directly transmits force input to the aileron feel and centering unit, whereas the first officer's control wheel directly transmits force to the spoiler mixer. The spoiler mixer is further discussed in the secondary flight controls lesson. In case there's a failure or jam in either control wheel, the aileron transfer mechanism allows for both control wheels to be able to make roll commands. For example, if the spoiler system is jammed, aileron roll control may be achieved through the captain's control wheel. However, the first officer's control wheel and the flight spoilers would then be unusable. On the other hand, if one control wheel cannot move, the mechanism allows the other pilot to operate the other control wheel satisfactorily. The ailerons also have a trim system that works similarly to the elevator trim system, except that there is no trim wheel. Instead, 2 aileron trim switches are located in the aft electronic panel, and the aileron trim indicator is located on the top of the aileron control wheel. The indication is in units of trim, where each unit is equal to 6 degrees of control wheel rotation. The maximum trim available is 9.5 units, or 57 degrees, of control wheel rotation. When the aileron trim is in operation, an actuator moves the same aileron roller that we discussed before, causing springs to extend. This gives input to the power control units to move the ailerons, and the control wheels are also moved. Both aileron trim switches must be operated at the same time to supply power to the trim actuator. We saw before that the elevators and their systems were virtually in a straight line from the control columns in the cockpit. This is not the case with ailerons, where many of the components are located away from the airplane's fuselage. The very ailerons are located on the outboard trailing edges of both wings. This requires complex component linkages, which are achieved in the following way. The systems that run along the center line are connected to aileron body quadrants near the forward bulkhead of the main landing gear wheel well. Both body quadrants are connected to each aileron PCU. If one hydraulic system is off, the other PCU commands both quadrants. The body quadrants are connected to the wing quadrants through the wing cables. So when a wing cable moves, it moves the related wing quadrant and finally the respective aileron. Similarly to the elevators, there's an aileron tab that moves in a direction opposite to aileron movement to maintain positive balance. For example, when the control wheel is moved to the left aileron rises and the left aileron tab comes down. In the opposite wing, the right aileron comes down and the right aileron tab rises. This induces a noticeably higher angle of attack in the right wing when compared to the left wing, thus causing the right wing to go up and roll the aircraft towards the left. The ailerons also have balance panels and weights in order to decrease the force necessary to move them during flight. Flight spoilers are used to achieve significantly higher rolling moments around the airplane's longitudinal axis. These are a series of panels on the upper surface of each wing that rise when extended, thus creating an enormous amount of drag. Flight spoilers are only meant to be an aid to roll control, not the primary roll control method. There are 12 spoilers on each wing, numbered 1 to 12 from left to right. The most outboard and the most inboard spoilers on each wing are ground spoilers. Only the 4 flight spoilers on each wing provide roll control. During roll, when the control wheel turns left, the flight spoilers on the left wing move up, and in the right wing, they stay fared down. Flight spoiler panels on the 737NG have numerous functions, such as aiding ailerons in achieving roll control, aileron trim, speed brake operation during flight, and speed brake operation on ground during landing. Similarly to ailerons, the flight crew uses the control wheels to control roll with spoilers. The control wheels give mechanical input to the aileron power control units, PCUs, through the aileron feel and centering unit. From here, the PCUs supply mechanical input to the flight spoiler actuators that use hydraulic power to move the flight spoilers. The control wheels must be displaced more than 10 degrees left or right to actuate the respective set of flight spoilers. System redundancy is provided in the following manner. Each hydraulic system powers a specific set of flight spoilers in such a way that there's no asymmetrical deployment when there is a hydraulic system failure. One-sided deployment of spoilers is also avoided with this redundancy. Although most of the aileron operation seems difficult to understand and may need several reviews before it sinks in, keep in mind that most of what you've learned here will be transparent to you as the pilot flying. Having an understanding of the background workings of these systems may give you a greater appreciation for what goes on behind the scenes and what happens when things go awry. The rudder is a movable surface attached to the rear spar of the vertical stabilizer that provides yaw control of the aircraft around its vertical axis. The rudder may be operated by any of 3 ways: manually with the rudder pedals, manually with the rudder trim, or through the yaw damper. The yaw damper will be discussed in the following section. During manual operation, the pilot presses the pedals to achieve movement in the respective direction. For example, when the right rudder pedal is pressed, the rudder moves to the right of its neutral position, thus creating a rightward turning moment and achieving yaw to the right. The same logic applies when the left rudder pedals are pressed. Similarly to the rest of the flight control surfaces we've covered, rudder pedal movement inputs are linked to control valves in the rudder power control unit, PCU, via cables and linkages that also pass through the rudder feel and centering unit. In the case of rudder control, the pilot inputs are also linked to a standby rudder PCU that provides backup and system redundancy in the event of main rudder PCU malfunctions. There's no manual reversion available for rudder control, which means that if theoretically both normal hydraulic systems and the standby hydraulic system were to fail, rudder control would not be achievable. The probability of this happening is negligible. We mentioned earlier that elevators and ailerons had a pair of PCUs to control them. During normal operation, only one main PCU powers the rudder. The original 737 was designed using one dual valve with input from both hydraulic systems. This was partly responsible for a series of accidents associated to 737 rudder problems. In 2003, the Rudder System Enhancement Program, RSEP, was introduced, where the original dual valve that received input from both hydraulic systems A and B was replaced by one set of components and actuators for hydraulic system A, and an independent set of components and actuators for hydraulic system B. In this lesson, we'll discuss the rudder system schematic with RSEP installed. Both hydraulic systems and the standby hydraulic system have separate control input mechanisms for the rudder PCU. All three of them have individual jam protection mechanisms. When either system A or B is jammed or disconnected, the main rudder PCU detects a pressure imbalance via the Force Flight Monitor, FFM. It's important to understand this because the FFM, after 5 seconds, automatically turns on the standby hydraulic pump, standby rudder shutoff valve, and pressurizes the standby rudder PCU. Lights and annunciators are displayed in the cockpit when this condition occurs. The rudder has a maximum deflection of 29 degrees left and 29 degrees right. The rudder feel and centering unit gives simulated feel to the rudder pedals and centers the rudder and rudder trim inputs in the rudder PCU. When a pilot presses his rudder pedals, a roller is moved and springs are compressed, supplying feel force to the pedals. When the pedals are released, the roller moves to a detent and the system moves to a neutral position. The rudder may also be operated manually through the electric rudder trim control. This changes the rudder neutral position. One of the two rudder trim switches inside the single rudder trim control is connected to the Flight Data Acquisition Unit, FDAU, to record rudder trim position. The rudder trim indicator shows the amount of rudder trim in units. Rudder authority is limited when airspeed is higher than 137 indicated knots, in order to provide protection after takeoff and before landing. Dutch roll is an aircraft movement where the tail moves from side to side when there is input in the ailerons or rudder. In smaller aircraft, this condition is partially dampened. However, in larger aircraft, auxiliary systems like the yaw damper on the 737 NGX are used. This is due to the faster airspeed and higher altitude at which they fly. Yaw damper systems give input to the main and standby rudder PCUs via valves and actuators. The yaw damper actuator input is mechanically added to rudder pedal inputs. Both inputs may move the rudder PCU piston and the rudder. However, rudder input from the yaw damper is not reflected in rudder pedal deflection. The yaw damper system is made up of a main and standby yaw damper. The main yaw damper is powered by the hydraulic system B, and the standby yaw damper is powered by the standby hydraulic system. The yaw damper's system functions are turn coordination, gust lock prevention, and Dutch roll prevention. We've had a look at different flight control surfaces and systems on the 737NG. Now, we're going to discuss two of the three primary main use components, which are flight control cables, flight control panel, and flight control hydraulic modular packages. These won't be discussed in this lesson as they don't directly interface with flight crew or affect the airplane's operation. Flight control cables are used to give mechanical input to each feel and centering unit, then to each power control unit, PCU. The feel and centering units provide artificial feel forces to the controls and pedals, and also sets them to neutral positions. The PCU is responsible for directing hydraulic fluid in order to achieve control surface movement. Both these components were discussed in the respective sections of this lesson. The flight control panel, located in the forward overhead panel, has a series of hydraulic control switches and caution lights for the flight control systems. These are flight control switch, 2 switches, 1 for each hydraulic system, with 3 positions: on, off, standby rudder. The flight control's shutoff valve is powered by a 28-volt DC motor. On position is the normal operating position. Hydraulic system pressure is on to the elevators, elevator feel computer, ailerons, and rudder. Off position. Hydraulic system pressure is removed from the elevators, elevator feel computer, ailerons, and rudder. Standby rudder position. It has the same effect as the off position, but instead turns on the standby hydraulic pump and pressurizes the standby rudder PCU to achieve standby rudder control and standby yaw damper. Flight spoiler switch. 2 switches, 1 for each hydraulic system, with 2 positions, on and off. A 28-volt DC motor also powers them. The on position is the normal operating position. Hydraulic system pressure is on to the flight spoilers. And the off position, which removes hydraulic system pressure from the flight spoilers. The flight control low pressure light is a warning switch that gives an amber light indication when there's low hydraulic system A or B pressure to the flight control system. The low pressure light only operates when the flight control switch is in the on or off position. When the switch is in the standby rudder position, the standby rudder shutoff valve controls the low pressure light through the valve position relay. The low pressure light comes on when system pressure is less than 1300 psi. When the low pressure light comes on, there is a master caution and also the flight control annunciator comes up. Yaw damper switch and warning light, which has 1 switch with 2 positions, off and on. In the on position, it engages either the main yaw damper to main rudder if the B flight control switch is in the on position, or the standby yaw damper to the standby rudder PCU if both the A and B flight control switches are in the standby rudder position, or the off position, which disengages yaw damper. The yaw damper warning light comes on when the system is disengaged. Standby hydraulic low quantity and low pressure lights. These lights come on when the standby system reservoir hydraulic fluid quantity decreases below 50% of its normal quantity. The standby low pressure light comes on when the standby system output pressure from the standby electric pump decreases below limits. Flight control panel warning lights. These are certain warning lights that illuminate when unwanted flight control conditions exist. 1. Field differential pressure light. Comes on when there's a 25% difference between the System A and System B metered output pressures in the elevator feel computer for more than 30 seconds. 2. Autoslat fail light. This comes on when the autoslat function becomes unavailable. 3. Speed trim fail light. This comes on when the speed trim function in the flight control computers, FCCs, becomes unavailable. 4. The Mach trim fail light, which comes on when the Mach trim function in the FCCs becomes unavailable. Alternate flaps arm and control switches. This series of control switches are discussed in the secondary flight controls lesson. The 737NG has a complex flight control system, as we've seen during this lesson. There are several essential components and systems. We've also discussed the overall redundancy provided for flight controls. Unlike other early aircraft like the DC-10, the 737NG is very reliable in terms of keeping the aircraft in control during a hydraulic system failure, or control column jams, amongst other problems. The mechanical linkages for ailerons and elevators allow for operation with no hydraulic power through manual reversion. However, we also mentioned that operation becomes difficult because the amount of pilot input necessary to produce flight control surface movement is considerably large. We also discussed a few of the aids that pilots have in order to minimize pilot force input during normal conditions, such as the flight spoilers, yaw damper, and the horizontal stabilizer trim. We encourage you to investigate about the 737 rudder problems and send us your views in the comments section of this video. This lesson covered the following topics: an overview of the aircraft's three principal axes and the control surfaces that act on each one of them, basic physics of control surfaces, in other words, moments of force, primary flight controls on the 737 NGX for pitch, roll, and yaw, horizontal stabilizer trim, flight spoilers, yaw damper, the Mach trim system, speed trim system, 737 historic rudder problems and RCEP, and the 737 NGX flight control system components. In the next lesson, we'll learn about the secondary flight controls. Until then, throttle on.